My name is Abhinav Pagadala, and I'm a current graduate research assistant working in the Agricultural and Biological Engineering Department at the University of Illinois, Urbana-Champaign. Today, I'm incredibly excited to talk about our research regarding precision mechanical robotic weeding for specialty crops, an AI-based weed management system for horseradish. To start, I'd first like to talk about the team a little bit. The leaders of this project are Dr. Sunil Shahjahan and Dr. John Reed. Additionally, we have Elizabeth and Dennis who have worked tirelessly to ensure that we have effective communication between ourselves and the farmers. Finally, we have the graduate students who have been working for a long time, ensuring that we deliver high quality, impactful research. Pavan, John Majay, Sandesh, and myself. So why horseradish? Illinois is actually the #1 producer of horseradish in all of the United States. Around 1,700 of the 3,000 acres are harvested by just 27 Illinois farms. We actually have Collinsville and Madison County, which are actually known as Horseradish House, and over a majority of horseradish production is done just by Illinois. A challenge that these farmers are dealing with is the lack of mechanization. As you can see from this image, farmers have had to create a system where they utilize bike tires and weld tools onto them, then connect that up to some kind of tractor, and then utilize that for row marking and bed preparation. After they've done so, they then go through by hand and place roots in these beds. Afterwards, they then cover it up, ensuring that the process is complete. This is something that's incredibly time consuming and very inefficient. Another problem that they're dealing with is actually weed management. We need to fix this problem for them as it helps them maximize profit and revenue, and also just be more efficient. Current weed management techniques relies heavily on manual labor, something that's, of course, labor intensive, but also very cost intensive. And so for us, we want to develop a system to essentially fully automate a weeding robot for horseradish production. And to do this, we split this project up into 4 different steps. The first is a data collection process. Next, the autonomous navigation. Third, we have weed detection. And finally, we have our actuator mechanism. The most important step of our project is ensuring that we have high quality data. Each remaining component relies heavily on good data as these models are utilized throughout. The 3 image collection methods that we have are first the manual proximal camera, where an individual traverses the field with just an iPhone camera. Next, we have drone imagery, where a user operates the drone at a constant altitude and a constant speed, and then traverses the drone through the horseradish field, taking video files. And finally, we have a pre-built robotic system known as the Amiga, also used for data acquisition purposes that already has 2 cameras, operated by a user through the field in which video files are then captured. The next part that we worked on is actually the autonomous navigation. Pavan and Janmeja have worked tirelessly to ensure that we have an effective navigation system. As you can see from the video, cameras are able to detect horseradish rows, and then the robot is then able to move through the field effectively while not ruining the crops, but also staying in range for the actuator system to eradicate weeds. Here are more instances of our autonomous navigation in action. These videos are from more preliminary stages, but are just as effective in demonstrating our capability to develop autonomous navigation courtesy of Pavan and John Major. Next component that we want to handle is actually weed detection. This was done via annotating and augmenting each image utilizing a pre-built system known as RoboFlow. We were also then able to create a preliminary model utilizing YOLO V8, which yielded an accuracy of around 79%. This is something that we plan to improve. We've already discussed and utilized emerging technologies such as YOLO 11 and YOLO V12 and have begun training and analyzing those models for improved efficiency and accuracy. Here's a proof of concept that we were able to create that utilizes an object detection model. The screen is essentially split up into columns, and where a weed is located, we then turn on and off the actuator system accordingly to then send a signal to the actuator mechanism to eradicate the weed. The next critical component is the actual actuator mechanism. As you can see, we utilize a pneumatic, and when a weed is detected, we then drop the tailing mechanism and drag it over the weed. Once the weed is then tilled, the actuator mechanism then lifts up accordingly. Here's a recent video that was actually taken of the actuator mechanism in action. Once the weed is detected, it drops the actuator mechanism, impaling the dirt, and then it drags the weed out. And then once the weed has been successfully removed, the actuator mechanism then lifts up. In conclusion, for the last 7 months, we've actually tested navigation, detection, and actuation in a controlled setting. The next steps for us are first to collect more field data. Ensuring once again that we have high quality data is critical for our project, as each component relies heavily on successful and high accuracy object detection models. We also want to test navigation in the field while accommodating for challenges such as soil, slippage, and shadows. For weed detection specifically, we already are planning and utilizing new and emerging technologies, YOLO 11 and YOLO V12. These models incorporate good trade-offs between accuracy and also computational efficiency, which is very critical for our component given our constraints. We also want to explore other emerging object detection technologies such as RF DETR, which yields us similar accuracy but at a fraction of the training cost. In terms of actuation, we also want to try multiple arms and also swivel capability to reach within rows. And finally, an integration of all components. This is going to be a huge challenge, but given the effort and given the teammates that we have available, we're confident we can achieve this goal. Our vision is for farmers to independently implement this in the field and efficiently manage weights by themselves. A huge thanks to AI Farms for supporting and funding this project. We're also very excited to continue supporting and collaborating with these farmers to deliver high quality and impactful research. Please don't hesitate to reach out to me or Dr. Sinoj Shahjahan if you have any questions or concerns or any suggestions. Thank you very much for your time.